right, so last time we worked on multiplication algorithms. Without looking at your notes, everybody look at my eyes. What was one of them?
Lattice.
Lattice. What else?
Partial products.
That was cheating, Megan. Partial products is one of them. And there was someone that was called something like expanded notation or something like that, right? It just sort of explained what happens when you do your standard algorithm. But the two that were really, useful perhaps are lattice and partial products. Okay. We have two algorithms for division. One of them is your standard algorithm, so there's really only one new algorithm. This one new algorithm is called repeated subtraction. And depending on what you're dividing, it can be very quick or it can be really long. And it just depends on the numbers that you're working with. The benefit to repeated subtraction, it is a benefit, but in a bad way. The benefit is you don't really have to know your multiplication tables to do repeated subtraction. And in order to do our standard algorithm, you need to know your multiplication tables, right? Because you have to look at this and say, how many times does 5 go into 6? How many times does 5 go into 12? How many times does 5 go into something? And you actually have to know some of your multiplication tables to do that, right? Well, with repeated subtraction, you actually don't. So let me show you what repeated subtraction looks like. What we do with repeated subtraction is we subtract multiples of the value we're dividing by. So here's 5. A multiple of 5 is going to be multiples of multiplied by 10. So 5 times 10, which is 50. We can do 5 times another power of 10, 100. So we get 500. Yes, it has to be power to 10 for it to be repeated subtraction. And the reason is because, like I said, it doesn't require the idea of being able to multiply. Yeah, there we go, I'll stop. So I don't have to really multiply much, right? I had to multiply 5 times 1, and that's 5. And then I just fill the zeros on there. So repeated subtraction has this sort of a flavor to it that there's really not any multiplication table knowledge necessary. So I'm going to subtract the biggest one of those that I'm able to subtract, and that is 500. And onto the side, I'm going to write that what I just did was I did 5 times 100, just as a note to myself more than anything, and it'll help me with the solution when I'm done. Okay, so when I subtract, what do I get? 120. Now, if the number were large enough, I would subtract 500 again, but it isn't. So what's the next value I would subtract? 50. And why am I using 5 and 10 and 50, or 5 and 50 and 500? Multiplied by 5. And why did we multiply by 5, Marissa? That's right. So it's all based on what the division is by. Okay, so if this had been a 7, we would be doing 7 and 70 and 700, right? If this were a 3, we'd be doing 3 and 30 and 300 and 3,000 and so forth. Everybody clear on that? So I'm going to subtract 50. 50 was 5 times 10. What do I get? 70. So what can I subtract still? 50 again to give me 20. This is 5 times 10. All right, so what can I subtract now? 5. That's 5 times 1. And I get 15. And then 5. So there's 10. That's another 5 times 1. And then 5. And that's 5. And then I can do it one more time, right? Got to get to a remainder of 0 before I'm done. We're working with whole number division, which means they will all evenly divide, okay? So you don't have to, worry about, oh, what if I got a remainder of 2? There's no remainders in what we're looking at in this section, okay? It's all whole numbers. All right, so the question then in looking at all this is, well, what's my answer? I mean, I subtracted until I didn't have anything left, but what's my answer? Well, my answer is actually these numbers added together. And as you notice, they're all powers of 10, which means the addition's really easy, right? I've got 100, I've got 2 10s, which is 20, and I've got 4 1s, which is 4. So this is 124. So you can imagine if I had to subtract something 9 times, this would be a pain, right? I mean, I don't want to subtract this 9 times. But if I want to subtract it once or twice to get these all to flesh out, that works pretty well and pretty quick. And it really does require only subtraction. I don't need any multiplication. I don't really even need or see the traditional division that you think about when you say divide, do you? No. You just have subtraction. All right, so What our standard algorithm does is it actually does that repeated subtraction algorithm, but it does it in a condensed form. You just don't see it, right? So let's go through our standard algorithm because you know it. And what we do is we look at this 5 and this 6 and we say how many times does 5 go into 6, and the answer is 1. And that's the same 1 for the 100, right? Because it really wasn't 5 into 6, it was 5 into 600, wasn't it? And this 1 where it's located is really number 100. And then I do the 1 times 5 and I have 5, and I get a remainder of 1, and that's still 100 left over. Okay? And then of course what you remember next doing is pulling the 2 down, right? And then you say, okay, how many times does 5 go into 12? And that's 2 times. So I shortcutted the repeated subtraction, right? Instead of subtracting 5, or actually 50, twice, I'm going to multiply the 5 times 2 and I get 10. But really there's a 0 down here. That's really 100 that I just found, 50 and 50 together, right, from the previous slide. So I subtract, and what do I have? 2. I'm down to the point where I really have 20. And if I know my multiplication tables, right, I know 5 times what equals 20? 4, right? So I don't really need to subtract 5 4 different times. If I know my multiplication tables, I can just shortcut this and I get 20 down here. And there's my remainder of 0. Okay, so when we do division, we really do repeat subtraction. But we join that with our knowledge of multiplication to allow it to be shortcut. Right? We don't have to have so much work involved, so much writing. Is that good? Okay. We're going to do some, I don't know, I guess you could say examples that involve problem solving, which we did back in chapter 1. You guys remember that? Problem solving. With some of the different ideas of multiplication and division that you saw happening here. Okay? So we have, how do you say that? I don't even know. I used to think it's straight out of your book. Is it 1? Okay, we'll say 1. I should have used the name out that I could pronounce. That would have been a smart idea. Juan saved 5340 in 3 years. If he saved $95 per month in the first year and a fixed amount per month during the last 2 years, how much did he save per month during the last 2 years? So you guys are going to tell me, you encounter this problem and you're trying to figure it out, and what do you do? Right. No! That will not help.
Well, then you would take 95 times 12.
Okay.
To figure out how much you got first year.
That sounds good. So we're going to figure out how much he got on the first year. His first year, he saved $95 a month, and there are 12 months in a year. And you're going to multiply this. Now, don't you dare grab a calculator. That's the whole point in this chapter, right? Multiplying and dividing and whatnot. So let me write it this way. So perhaps you decide you're going to do partial products and you draw a grid. Perhaps you decide you're going to do lots of multiplication and you draw that. I don't really care. If you want to use your standard algorithm, that's okay too. But you do need to know how to use all 3, because I'm going to ask you when you get to the test to do them specifically at different points, okay? So let's do just the standard algorithm for now. So what am I going to get? 10 and carry my 1. There's 19. Why do I write down this 0? But why is it a placeholder? Because, okay, so when I'm multiplying by 1 here in a moment, I'm not really multiplying by 1. What am I multiplying by? 10, because the 1 is in the tens place. Okay, so when I multiply by 10, I get a 0, and then I can multiply by the number 1, and I get 95. Add them up, and what do you have? Is it 1140 maybe? Yeah. Okay, sorry, I misheard. Yeah. Okay. So this is how much he saved his first year, correct? Now what? Sounds good. So the 5340 is what he saved in the total of the 3 years. I have 1140. And this is a really nice one. I don't even have to borrow to subtract this. What do you get? 4,200. Now what?
Could you divide it by 2?
We could divide it by 2. And what would that give us if we divide by 2, Caitlin?
12.
Sarah? Oh, I don't mean the number. Let me clarify what I meant. What would I be finding if I divide by 2?
How much you make in 2 years?
No. Per year. How much you saved per year in the last 2 years, right? Right, it would be telling us how much you saved in one of those last 2 years. Okay, so let's do that. That sounds good. So if I take 4,200 and I divide by 2, Sarah told me I get 2,100, which I do. I don't really even need a lot because there isn't really anything remaining as I subtract these, right? 2 times 4, and then I have the 2, and I subtract 2, and then I have zeros everywhere, okay? All right, so 2,100 here. So as you're working, you need to make sure you're telling me what in the world you have found, because you may have thought you found the answer and you haven't yet, because we're not done. So he saved $2,100 per year the last 2 years. But what did it ask me to find?
Per month.
How much did you save per month? So you divide it by 12. So did anybody else think to do this differently than to divide by 2 and then divide by 12? We could have just divided by 24, because there's 24 months in the 2-year span. It doesn't matter, but just thinking of another option or what another student might think is sometimes good to think about. So we have 2,100 now, and you guys want to divide by 12. Okay, so obviously 12 doesn't go into 2, but 12 does go to 21. How many times? Months. All right, 21 minus 12? 9. So now I have 90. How many times does 12 go into 90? It is 7. What is 7 times 12? Good job, 84, which is a remainder of 60, 6, and then I've got 0 for 60. And then how many times does 12 go into 60? 5. And it does go in evenly. So how much did he save per month the last 2 years? $175. So I don't think that one was worth crying over. You guys did that just fine. It turned out not so hard, huh? Okay, you ready for the next one? Dan. Dan has 4,520 pennies in 3 boxes. He says there are 3 times as many pennies in the first box as the third, and there are twice as many in the second box as the first. How much does he have in each box? So what are you going to do? Well, we're going to have something with the 3 in there, but I think we need to figure out how the 3 is affecting everything before we just divide by it.
3 times as many. So we multiply something.
We are going to multiply something. Can we draw a picture? Yeah. Because I don't know about you, but that's the first thing I did is I drew 3 boxes. This is what it said, right? We have 3 boxes. Here's box 1. Here's box 2, and here's box 3. And in reality, what I know is that if I add the number of coins in each box, it's going to equal the 4520, right? So whatever this is, kind of in my mind, I'm thinking add equals 4520. And I've got to figure out what numbers go in those boxes to make that work. And you could use trial and error, but I don't think it's going to be real helpful until you kind of establish some other ground rules first. In particular, it gives you some information about how many pennies based on other boxes. There are 3 times as many pennies in the first box as the third, right? So whatever is in box 3, we would multiply that by 3 to get the number of pennies in box 1. And then it says there are twice as many pennies in the second box as the first box. So whatever we find out for the first box, we would multiply that by 2 to get what's in the second box. What? Do you have an idea more?
Well, because I like put like in box 3, which 3 times is more in 1. And like if box 3 was just x, then in box 1 is 3x.
Okay.
And then box 2 would be 3x times 2. Right? 1 is 2x. 3x times 2 is 2 times 1. And then equals 45.
So algebra. This is what you told me, right?
Yeah.
I wrote it down right? Okay. So let's make sure it works with the description that it described, okay? How it described it. It says there are 3 times as many pennies in the first box as the third. So if the third box has x, then box 1 has 3x. That description works. Then it says there are twice as many in the second box. So here's this 2 times something, as in the first box. And the first box had 3x. So I think that works. Yeah. This looks really good because I can set up an equation now for this. And whether or not you used X's with a young child to do this, or you used little blank boxes, or you used something like that, you could still do this idea where you're adding things together. So we have 3x plus, which is 6x plus x equals 4,520. Can you simplify the left-hand side? 10x then what? Divide by 10. I like dividing by 10 because all it does is make numbers 1 digit less, right? So what is x? 452. So we need to make sure we answer the question, how much does each box have? So box 3 has 452 pennies. What else? Okay, so box 1 has, and if you take the 452 and you multiply by 3, okay, so I've got 6, we've got 15, 12, so there's my 1356. All right, so box 1 has 1356, then what? You could. What else could you do?
We can multiply box 1 and multiply 2. Right,
and we've already done, that part of that, so we might as well take box 1, which is 1356, times 2. 2 times 6 is 12, carry my 1. 2 times 5 is, plus 1 is 11, carry my 1. 2 times 3 is, plus 1 is, 2 times 1 is 2,712 pennies. How could we check to make sure this works? And it wouldn't be a bad idea, right, to make sure we didn't make a multiplication error. Yeah. We can add them all together and make sure they actually equal 45. Make sense? Pictures are very helpful. All right. One more example. This is an interesting one because one of the descriptions, when I was doing my dissertation, I asked this question of the people that were involved in my study to describe math. So if you were to describe math, what would you say math is? And there's 2 common approaches to thinking about mathematics. There's others as well, but the 2 probably that are the most common is to think that math is patterns. It's all about patterns. Or to think about math as problem solving. And not to say that those sort of views don't overlap, they do, but those are 2 really common views of mathematics. This is a patterns one, okay? So we notice that the student observed that 39 plus 41 is 40 plus 40, right? Yes. Sure, no problem. We take 1 away from one place, add it to the other one, we get 40 plus 40. And so they asked, does 39 times 41 equal 40 times 40? So find out for me real quick, does it work? Grab a calculator on your paper, whatever you're going to do. I want you to multiply 39 times 41. and I want you to multiply 40 times 40. Now, what did you get on the 39 times 41?
1,100.
And then 40 times 40 is 16. Okay, so you can answer the student really quickly, right? So answer the student for me. No. And you can justify that by multiplying that and showing him that it doesn't work. So how do you reply? The answer, of course, is no. Because of this, right? We've shown that this doesn't hold this. We've got another student that instead of just asking an interesting question, because that's an interesting question, right? It works for addition, it didn't work for multiplication. So we've got another student, and you guys are going to have these students who are going to say things and you're going to be like, oh, you're going to have them in your classroom, whatever level you have, doing something, whether it's with math or reading or something about language, it may be something about science, and they're going to ask you something and you're going to be like, I'm going to have to get back to you on that. Because they're going to think outside the box, which is good thinking, okay? So this other student observes that if you take 39 times 41, while it doesn't equal 40 times 40, it's exactly one less than 40 times 40, right? And you see that, right? Because I've got 1600 and I've got 1599. And he also finds that if you do 49 times 51, then you can do the same thing. You get 50 times 50 minus 1, and it works. And so he wants to know if this pattern continues. When would it be true? How do you respond? So what kind of things do you do? Well, first of all, you got to figure out if it does continue. So for the practical purposes of working with a young child, you can try a few of them, right? And you can probably pretty well convince yourself that it works. But it only works in certain cases. For example, let's say that you did, so if you wanted to do, for instance, 39 and 41, they did that one. This is 49 and 51, 69 and 71, okay? But what if we did something like 48 and 35? Can you increase one of those and decrease the other one and subtract one? Will that work? That's sort of the question. And it doesn't work quite that well. So I want to show you this because it's an interesting idea. I don't even know if I have the space. I'm going to have to increase my screen. So let's see what we're doing. What we're really doing is we're multiplying two numbers together. So let's say that we're multiplying. So this isn't what you show a student, but I'm not saying that. But you're trying to decide, does this always work? And if so, what are the conditions upon which it's going to work? Because you don't want to tell the student, yeah, the pattern always works, and what you think he meant by the pattern and what he thinks he meant by the pattern are one and the same thing. You got to be real careful, right? Does he think the pattern is simply add one to one and subtract it from the other, or is there more going on? So let's say we have these two numbers, x and y, and we're multiplying them, right? What we want to know is if I were to increase one of them by 1, and I were to decrease the other one by 1, right? That's what they did. They took 49 and they increased it by 1. They took 51 and they decreased it by 1. And then I subtracted 1 from this. Are these going to equal each other? Because that's the question. Are they going to equal each other? Now, we've learned a fair bit in this chapter about distribution property, right? And you guys know the distribution property for two terms at a time called foiling, right? First, outer, inner, last. So let's find this out here because we're going to use those thinking skills. So if we FOIL this, what do we get? Minus x. So the xy's match, correct? So the issue is that this is only going to work if this piece right here equals 0. Right? What's that? Oh, no, I left it off. I'm sorry. I knew there was something not looking right. I'm sorry. In fact, yeah. There we go. Thank you. There's my equals 0. So, as you look at the x and the y, Let me take one more step to simplify this just a little bit over here. What I've actually got here then is negative x plus y has to we'll say equals 2. Okay, so I'm going to add the 2 to the other side. This is equal to 0 and I add 2. Okay. So the issue is that I have to have y minus x, I'm just rewriting it with a negative between them, equals to 2. So when will this work? Well, it will exactly work when the two numbers you're dealing with are 2 apart. So can I always add 1 and subtract 1? No. But if I've got two numbers that are only 2 apart to begin with, they don't even have to be the 9 and the 1. You know, it doesn't have to be 49 and 51, 39 and 41. The numbers I'm dealing with just have to be 2 apart. And for example, if I had 35 and 37, those numbers are 2 apart, right? So if I add 1 to 1 and subtract 1 from the other and I turn them into 36 and 36, and I multiply 35 times 37, and I multiply 36 times 36 and subtract 1, that'll work here too. Okay, so yes, the pattern continues as long as the two numbers you're starting with are exactly 2 apart. In other words, when I do the adding 1 and subtracting 1, I get the same number, right? 36 and 36. So that's something that's a little bit unique. There's visual representations for what we can show for that too, but you know, I guess what I want you to take away from this problem is not necessarily that your student's going to come up with this, but this sort of idea that your students are going to come up with something that you're not going to know how to deal with. And you're going to have to use math that's beyond their level of thinking to be able to answer that question. And you don't have to go through any of this algebra with the student, but you need to be able to tell him what his answer is. That yes, this pattern does continue as long as what he means by the pattern is that the numbers are 2 apart to begin with. You guys kind of follow me on that? All right, we'll stop there.